Okay, exponential functions on page 468 in your textbook, lesson 8-7. Here's a little intro for you.
See if you can figure out what these changes have in common. The amount of money accumulating over time in an education fund, the geometric construction of colorful shapes called fractals, the number of bacterial cells growing in a laboratory culture, and the amount of time it takes for soup to go from scalding to edible. All these changes can be described by exponential functions. Indeed, exponential functions are used to describe those and other interesting processes in fields such as chemistry, biology, physics, economics, and finance. We'll delve into some of those applications, but first, let's become acquainted with these functions. And the graphing calculator can help us. We'll discover properties of exponential functions and graphs, explore an application of exponential growth, and an application of exponential decay.
Okay, on page 468, you'll notice that we have a formula. An exponential function is a function in the form y equals a times b to the x, where a is a non-zero constant and b is greater than 0 but not equal to 1, and x is a real number. Okay, let's put that function form. Y equals a times b to the x. Okay, and they give you a couple of examples. Y equals 1/2 times 2 to the x, or f of x, oh, we're going back to function notation, equals -2 times 0.5 to the x. That brings up our point of domain and range. Remember, domain is our input and range is our output. So in this particular function, x is going to be the domain, and y, or f of x, becomes the range. Okay, remember input, output. We're going to be talking about domain and range. You need to know how to use those terms interchangeably with input and output. Okay, we're just going to do some evaluation of some of these functions. When we're evaluating functions, we're just going to create a table. Okay, we're going to put our x here. We're going to put the value, or what we're doing the function machine on, and then the y value over here. In this particular case, this is quick check number 1 on page 468. And it asks us to evaluate each function for the domain. So my domain has to be -2, 0, and 3. Okay? So that means my x values here are going to be -2, 0, and 3. So I'm going to go over here and I'm going to substitute in. So it's 4 to the -2 power, 4 to the 0 power, and 4 to the 3rd power. Okay? Now we know that when we have something to a negative power, it becomes 1 over 4 squared, or 1 over 16. That's my y value. 4 to the 0 power, anything to the 0 power is always uno, eins, 1. And 4 to the 3rd power. Remember, I told you it would be a good idea to know your cubes, because 4 to the 3rd power is 64. That's all we're doing when we're evaluating these functions. Let's look at f of x equals 10 times 5 to the x. Okay, we're going to have an x. We're going to have a 10 times 5 to the x, and then we're going to have an f of x value. Again, we're using the same domain. My domain is going to be -2, 0, and 3. Brackets, not parentheses. Okay, so for my x values, I put in -2, 0, and 3. So when I substitute, here I go. 10 times 5 to the -2nd, 10 times 5 to the 0, 10 times 5 to the 3rd. Okay? We know that 5 to the -2nd is 1 over 5 squared, so this becomes 10 times 1 over 25, or 10/25, which becomes 2/5. 10 times 5 to the 0 is 10 times 1, which is 10. And then 10 times 5 to the 3rd. Okay, another time where we're cubing. 5 to the 3rd is 125 times 10, 1250. Okay, evaluating these expressions, or these functions. Okay, let's apply this. Okay, on page 469, we have a real-world example where it's talking about 20 rabbits are taken to an island, and the rabbit population begins to triple every half year. The function f of x equals 12 times 3 to the x power, where x is the number of half-year periods, models our situation. How many rabbits would there be after 2 years? Look at that. In red is 4. How come they used 4 instead of 2? Write that down. Now we're going to go on to quick check 2. Suppose 10 animals are taken to the island, and then the population of these animals quadruples every year. Use the function f of x equals 10 times 4 to the x power. How many animals would there be after 6 years? Okay? So we have this function, f of x equals 10 times 4 to the x, where f of x is representing animals and x is representing years, because it quadruples in a year. So I'm going to substitute here. I'm going to have 10 times 4 to the 6. What is 4 to the 6th power times 10? We know 4 cubed is 64. So 4 to the 6th is 4,096. So 10 times 4,096 equals 40,960 rabbits. Okay, a lot of bugs buttons. All right, let's move on and let's talk about what would this look like if we graphed it. Okay, here you'll notice, and you'll notice in the middle of page 469, exponential graphs. What do you notice about them? Describe their appearance. Their appearance is a what? Look at what's happening here. They're a curve. We need to remember from our past experiences, continuous versus discrete data. Continuous data, lines are connected. Discrete data, lines are not. You need to be able to know, should your graph show continuous data or discrete? Let's look at example 3. We're going to graph this function, y equals 1/2 times 2 to the x power. When we get ready to graph functions, I feel like it's easiest to make a t-chart with my x and y values. How many points do I ask that you put? 3. Let's try a negative number. Let's try -2, 0, and a positive number. Now we're going to evaluate. 0.5 times 2 to the negative second power, 0.5 times 2 to the 0 power, and 0.5 times 2 to the second power. Okay? 1/2 times 2 to the negative second power. 2 to the negative second power is 1 over 2 squared. 1 over 2 squared is 1/4 times 1/2. That is 1/8. 1/2 times 2 to the 0. 2 to the 0 is always 1, so that is 1/2. Half of 2 squared. 2 squared is 4. Half of 4 is 2. Here are my ordered pairs. So I'm going to go to my graph, and we're going to graph these. -2, -2, 1/8. Okay, 0, 1/2, and 2, 2. And we just discovered that exponential graphs, functions, are a curve. You may want to pick another point up higher, but you know that it's going to be somewhat like this. Okay? Why did I make this one continuous? Why didn't I even question whether it be continuous or discrete? Could I have put in fractional points for my exponent? Yes. Is it possible to get fractional results? Yes. Therefore, it is continuous. Look over example 4. It's talking about a photocopier that's making enlargements. Notice that graph is discrete. Why? Be able to tell me that answer, as well as why we used 4 instead of 2 in example 2, and your guided practice for tomorrow.